Somewhere out there, beyond the quiet glow of your screen, beyond the ceiling above you, beyond even the faintest stars you might glimpse on a clear night, the universe continues, endlessly, silently, expanding into something we still don't fully understand. And tonight, we're going to explore that, slowly, carefully, and just a little differently than you might be used to. Before we begin, take a moment to settle in. Wherever you are in the world right now, I'd genuinely like to know. Drop a comment about where you're listening from. And if you enjoy this kind of calm, thoughtful exploration, the kind that doesn't rush to answers, but instead sits with the questions, consider subscribing. This channel is a place for people who like to think a little deeper, who are comfortable with uncertainty, and who don't mind letting their curiosity wander into the unknown. Now, let's begin with something simple. What is the universe? At first glance, that might seem like a question we've already answered. Modern cosmology tells us that the universe began approximately 13.8 billion years ago with what we call the Big Bang, a rapid expansion from an extremely hot, dense state. Since then, space itself has been stretching, carrying galaxies along with it, like distant islands drifting apart on a vast cosmic ocean. This explanation is supported by multiple lines of evidence: the cosmic microwave background radiation, the observed redshift of galaxies, and the abundance of light elements like hydrogen and helium. And yet, even within this widely accepted model, there are quiet uncertainties, small gaps that don't quite resolve as cleanly as we might expect. For example, when we say the universe began, what do we actually mean by that? The Big Bang model describes the expansion of space, but it doesn't necessarily explain the origin of the initial conditions themselves. In fact, if you follow the equations of general relativity backward, you reach a point of infinite density and temperature, a singularity. But singularities, as physicists often admit, are less of an answer and more of a signal that our current understanding breaks down. So already, right at the beginning, we encounter something interesting. The most widely accepted explanation of the universe's origin contains within it a boundary, a place where physics, as we know it, stops working. And this is where things begin to quietly open up. Because if our current models cannot fully describe the beginning, then we are left with possibilities. Not wild, ungrounded fantasies, but careful, structured alternatives that attempt to fill in those gaps. One such idea is that the Big Bang was not the true beginning, but rather a transition, a phase change from a previous state. Some physicists have proposed cyclic models where the universe expands and contracts over immense timescales, effectively resetting itself. Others suggest that our universe might be just one bubble within a much larger multiverse, each bubble with its own physical laws and constants. Now, it's important to pause here and be clear. These are not confirmed realities. They are hypotheses, extensions of existing theories, built carefully from mathematics and observation, but still awaiting evidence. And yet, they exist for a reason. Because when scientists examine the universe closely, they notice patterns that are unusually precise. Take the fundamental constants of physics, values like the strength of gravity, the charge of the electron, or the cosmological constant. If even one of these were slightly different, just a fraction of a percent, the universe as we know it would not exist. Stars might not form. Chemistry might not work. Life, at least in any recognizable form, would be impossible. This is often referred to as the fine-tuning problem. The mainstream explanation typically leans on probability and selection bias. We observe these constants because we exist in a universe where they allow observers to form. In other words, it's not surprising that the universe supports life, because if it didn't, we wouldn't be here to notice. It's a logical argument, but it doesn't fully remove the sense of improbability. And this is where alternative interpretations begin to quietly emerge, not as conclusions, but as questions. If the universe appears finely tuned, is that simply a result of chance across countless universes? Or does it suggest some deeper underlying principle that we haven't yet discovered? Could there be laws governing the laws themselves? Meta-rules that determine how universes come into being? Or perhaps more subtly, are we missing part of the picture entirely? Because when we look at the universe, we're not seeing it directly. We're interpreting signals, light that has traveled for billions of years, filtered through instruments, translated into data, and then into models. Every observation we make is, in a sense, a reconstruction. And sometimes, those reconstructions reveal something unexpected. Consider dark matter and dark energy, two components that, according to current models, make up about 95% of the universe. Dark matter is inferred from gravitational effects. It seems to hold galaxies together, preventing them from flying apart. Dark energy, on the other hand, appears to be driving the accelerated expansion of the universe. But here's the curious part. We've never directly detected either of them. We know something is there. The evidence is strong, consistent, and widely accepted. But the true nature of these components remains unknown. They don't emit light. They don't interact in ways we can easily measure. They are, in a very real sense, invisible. So when we say we understand the universe, what we really mean is that we understand about 5% of it with confidence. And the remaining 95%? It's labeled, categorized, mathematically described, but not truly understood. Now again, the mainstream scientific approach is cautious. Researchers are actively working to detect dark matter particles, to refine measurements of cosmic expansion, to test new theories that might unify these observations. This is careful, methodical work. But from a broader perspective, it raises an interesting possibility. What if the universe is not just stranger than we imagine, but structured in a way that limits what we can perceive? Not intentionally, not by design necessarily, but as a natural consequence of how reality operates. There's a concept in physics known as the observable universe. Because light travels at a finite speed, there is a limit to how far we can see, about 46 billion light years in any direction. Beyond that, there may be more universe, potentially infinitely more, but it is forever beyond our observational reach. So even in principle, there are regions of reality we will never access. And this creates a subtle but important shift in perspective. Because it means that any model of the universe we construct is inherently incomplete, not wrong, not useless, but partial. A map drawn from within the system, never able to step outside and view the whole. And when you begin to think about it that way, the universe starts to feel less like a solved puzzle, and more like an ongoing investigation. A system where each answer leads to new questions, where every layer of understanding reveals another beneath it. So tonight, as we begin this journey, we're not going to rush toward conclusions. We're not going to claim hidden truths or secret knowledge. Instead, we're going to do something quieter and perhaps more interesting. We're going to look carefully at what we know. We're going to notice where the edges are, where explanations become uncertain, where data leaves room for interpretation. And in those spaces, we're going to ask questions, not to prove anything, not to convince, but simply to explore. Because sometimes, the most intriguing part of the universe isn't what we can see, but what we can't quite explain yet. And as you continue to listen, as your thoughts begin to slow and drift, keep this in mind. Everything we're about to explore exists somewhere between certainty and mystery, a place where science is still working, and where curiosity has plenty of room to wander. As we move a little deeper into this quiet exploration, it helps to shift our focus, not to the beginning of the universe this time, but to its structure as it exists right now. Vast, layered, and in many ways, unexpectedly organized. At the largest scales we can observe, the universe is not random. This is one of the more surprising discoveries of modern astronomy. If you map out the positions of galaxies across billions of light years, a pattern begins to emerge. Not a simple one, not something immediately obvious, but something unmistakably structured. Galaxies cluster together in long filaments, forming what scientists call the cosmic web. Between these filaments are enormous voids, regions of space so empty they contain very few galaxies at all. 4. The mainstream explanation for this structure is grounded in gravity and time. After the Big Bang, tiny fluctuations in the density of matter, barely perceptible differences, began to grow under the influence of gravity. Regions that were slightly denser pulled in more matter, becoming even denser over time, eventually forming galaxies and clusters. Meanwhile, less dense regions became emptier, expanding into the vast voids we see today. It's a beautiful explanation, elegant, consistent, and supported by simulations that closely match what we observe. But as always, when you slow down and really look at it, there are details that invite further thought. For instance, the scale of this structure is almost difficult to comprehend. These filaments stretch across hundreds of millions of light years. The voids between them are equally immense, and yet, despite this enormous scale, the pattern repeats. There is a kind of self-similarity, structures within structures, clusters within clusters. Some researchers have even pointed out that, in certain visualizations, the cosmic web bears a striking resemblance to networks found on much smaller scales, such as neural networks in the brain. Now, to be clear, this does not mean the universe is a brain, or that galaxies are somehow thinking. The resemblance is visual and structural, not functional. The mainstream view treats this as a coincidence, an example of how similar patterns can emerge from different processes, a concept known as scale invariance. But it does raise an interesting question. Why do certain patterns repeat across such vastly different scales? In physics, this kind of repetition often points to underlying principles, rules that apply universally, regardless of size. Fractals, for example, display self-similarity across scales, and they arise from relatively simple mathematical rules. So one possibility is that the universe's large-scale structure is simply the natural outcome of gravity acting over time, following predictable laws. But another possibility, more speculative, but still grounded in observation, is that there may be deeper organizing principles at work. Not necessarily intentional or designed, but fundamental in a way we don't yet fully understand. And this brings us to something even more subtle. Because when we observe the cosmic web, we are not directly seeing the majority of the matter that forms it. Most of the structure is thought to be shaped by dark matter, the same unseen component we mentioned earlier. Dark matter does not interact with light, which means we cannot observe it directly. Instead, we infer its presence through gravitational effects, how galaxies move, how light bends around massive objects, how structures form over time. So in a sense, the visible universe, the stars, the galaxies, the glowing clusters, is just a kind of surface layer. Beneath it, or perhaps around it, is a much larger, invisible framework. And that framework appears to dictate the arrangement of everything we can see. Now, the standard interpretation is straightforward. Dark matter provides the gravitational scaffolding for structure formation. Without it, galaxies would not form the way they do. Simulations that include dark matter match observations far better than those that do not. But again, there is a quiet gap here, because while we can model dark matter's effects with impressive accuracy, we still don't know what it is. Various candidates have been proposed, weakly interacting massive particles, axions, even modifications to gravity itself. but so far, none have been definitively confirmed. So we find ourselves in an interesting position. We are describing the structure of the universe using something we cannot directly detect, relying on its effects rather than its nature. And that's not unusual in science. Many discoveries begin this way. But it does mean that our current picture, as detailed as it is, rests on an incomplete foundation. And if the foundation is incomplete, it leaves room for alternative interpretations. Not replacements, not contradictions, but extensions. For example, some researchers have explored the idea that what we call dark matter might not be a particle at all, but rather a property of space itself, something emerging from the geometry of space-time under certain conditions. Others have suggested that our understanding of gravity might need adjustment at very large scales, leading to modified gravity theories. These ideas are still being tested, debated, refined, but they all point to the same underlying reality. We are still in the process of figuring this out. And there's something quietly fascinating about that. Because it means that the structure of the universe, the vast cosmic web stretching across unimaginable distances, is not just something we observe, but something we are actively trying to understand at a deeper level. And as we do, new questions naturally arise. For instance, why does the universe appear so uniform on large scales, despite its intricate structure? Measurements of the cosmic microwave background suggest that, in its earliest moments, the universe was remarkably smooth, almost perfectly uniform in temperature and density. Yet from that near-uniform state, such complex structures emerged. The mainstream explanation involves a period called cosmic inflation, a rapid expansion in the early universe that smoothed out irregularities while preserving tiny fluctuations that later grew into galaxies. It's a powerful theory, and it explains many observations. But inflation itself introduces new questions. What caused it? What mechanism drove this rapid expansion? And why did it stop? There are models, of course, fields, potentials, quantum effects, but none have been directly confirmed. So even here, in one of the most successful frameworks in cosmology, we find another boundary, a place where explanation transitions into hypothesis. And if you step back for a moment, you might notice a pattern forming. At every level, whether we're talking about the origin of the universe, its unseen components, or its large-scale structure, we encounter the same structure of understanding. A core of well-supported knowledge, surrounded by areas of uncertainty, and beyond that, a horizon of open questions. Not gaps in a negative sense, but spaces where exploration is still ongoing. And perhaps that's the most important thing to hold on to as we continue. Because it means that the universe is not a closed book. It's not a solved equation with all variables accounted for. It's something still unfolding, not just physically, but intellectually. Every observation, every new measurement, every refined model adds another piece, but never quite completes the picture. And so, as your thoughts begin to slow, as the vastness of these ideas settles in, consider this. The universe, in all its complexity, may not just be something we are observing from the outside. In a way, we are part of it. Small, localized patterns within a much larger system, trying to understand the system itself. And that creates a kind of loop. The universe observing the universe. A structure trying to map its own structure. And within that loop, there are limits. Not necessarily barriers, but natural boundaries to what can be known from within. So as we continue, we'll begin to explore those boundaries more closely. Not just the physical limits of observation, but the deeper question of whether there are aspects of reality that might always remain just out of reach. Not hidden, just beyond the edge of what can be fully grasped. As we continue moving outward, both in distance and in thought, it becomes necessary to confront a subtle but important idea, one that sits quietly beneath much of modern cosmology, yet is rarely considered in everyday discussions. It's the idea that there may be limits, not just to what we currently know, but to what we can ever know. Up to this point, we've been exploring the universe as something vast but observable, something that, given enough time and better instruments, might eventually be mapped in full detail. But that assumption begins to soften when we consider the nature of observation itself. Light, the primary messenger of the cosmos, travels at a finite speed. This is not just a technical detail, it fundamentally shapes our perception of reality. When you look at a distant galaxy, you are not seeing it as it is now, but as it was millions or even billions of years ago. The farther you look, the further back in time you see. This leads to a fascinating consequence. There is a boundary to how far we can observe, not because there is nothing beyond it, but because light from those regions has not had enough time to reach us since the beginning of the universe. This boundary defines what we call the observable universe. Beyond that boundary, there could be more. In fact, based on current models, there almost certainly is. And yet, no matter how advanced our technology becomes, those regions remain inaccessible, not because of a temporary limitation, but because of the way space-time itself is structured. So already, we are faced with a quiet realization. The universe is almost certainly larger than what we can ever observe. Now, the mainstream scientific approach acknowledges this without much discomfort. Cosmologists often treat the observable universe as a representative sample of the whole. If the laws of physics are consistent everywhere, and there is strong evidence to suggest they are, then studying our region should give us insight into the larger structure. But this assumption, while reasonable, is still an assumption, because we cannot verify it directly. We cannot step outside the observable universe and compare regions. We cannot confirm that conditions are identical beyond our horizon. We can only infer, extrapolate, and model. And this is where things begin to get interesting in a more philosophical but still grounded way, because it raises the question, how much of our understanding of the universe is shaped by what we can observe versus what actually exists? If we are limited to a finite region, then our models, no matter how precise, are based on incomplete data. They may be extremely accurate within that region, but they might not capture the full picture. This is not a flaw in science, it's simply a consequence of working within a system. And yet, when we sit with that idea for a moment, it introduces a different perspective. Because it suggests that there may be aspects of the universe that are not just unknown, but fundamentally unobservable. Not hidden in the sense of being concealed, but simply beyond the reach of any possible measurement. Now, to bring this closer to something more tangible, consider the expansion of the universe. Observations show that distant galaxies are moving away from us, and the farther they are, the faster they recede. This expansion is not like objects moving through space. It is space itself expanding, stretching the distances between galaxies. And here's where it becomes even more intriguing. Due to this expansion, there are regions of the universe moving away from us faster than the speed of light. Not because they are traveling through space at that speed, but because the space between us and them is expanding. As a result, light emitted from those regions will never reach us, ever, even given infinite time. This creates what is sometimes called a cosmic event horizon, a limit beyond which events can never influence us. So now we have two boundaries: the observable universe, defined by how far light has traveled since the beginning, and the event horizon, defined by the future limits of what can ever be observed. Between these boundaries lies everything we can, in principle, know. Beyond them lies everything else. And again, the standard interpretation is careful and measured. These are natural consequences of the laws of physics as we understand them. There is no implication of anything unusual or mysterious beyond the horizon, just more universe, governed by the same rules. But from a broader perspective, it introduces a subtle shift, because it means that reality, as a whole, may be far larger and potentially far more complex than any model we can construct. Not because our models are flawed, but because they are inherently bounded. And this brings us to another layer of consideration. Because if there are limits to observation, there may also be limits to explanation. In physics, many of our most successful theories rely on the assumption that the universe is, at its core, understandable, that with enough effort, we can uncover the rules that govern everything. And to a large extent, this has been true. From the motion of planets to the behavior of subatomic particles, we've made extraordinary progress. But as we approach the edges of our current understanding, whether it's the beginning of the universe, the nature of dark matter, or the structure beyond the observable horizon, we begin to encounter questions that may not have straightforward answers, not because they are unimportant, but because they may lie outside the domain of what can be tested or observed. And this is where science becomes something slightly different. Not less rigorous, not less valuable, but more open-ended. A process not just of finding answers, but of refining questions. And within that process, there is room for careful speculation. Not the kind that leaps to conclusions, but the kind that explores possibilities while remaining grounded in what we know. For instance, some physicists have suggested that the observable universe might be just a small region within a much larger, possibly infinite structure. Others have proposed that different regions of the universe could have different physical constants, a concept sometimes associated with the multiverse. These ideas arise naturally from certain interpretations of inflationary theory and quantum mechanics, but again, they remain unconfirmed. Not necessarily because they are incorrect, but because they may be difficult, or even impossible, to test directly. And so, we arrive at an interesting intersection, a place where science, observation, and speculation meet. A place where the boundaries of knowledge are not sharply defined, but gradually fade into uncertainty. And within that space, something subtle happens. Because instead of asking, "What is the universe?" we begin to ask, "What can we know about the universe?" And those are not quite the same question. One assumes a complete answer is possible. The other acknowledges that there may always be more beyond reach. So as you continue to listen, as the scale of these ideas settles into something quieter, consider this. The universe may not just be vast in size, but vast in possibility. Not every mystery is waiting to be solved. Some may simply be waiting to be explored from within the limits we have. And perhaps that's part of what makes this so compelling. Not the certainty, but the openness. The sense that, no matter how far we go, there will always be something just beyond the horizon, something inviting us to keep thinking, to keep questioning, to keep looking just a little deeper. As we continue, it becomes useful to gently shift our attention again, not outward this time, but inward, toward the smallest scales of the universe. Because just as there are boundaries at the largest distances we can observe, there are also limits at the smallest levels of reality. And interestingly, those limits may be just as important in shaping what the universe is and what it can be. When we look at matter in everyday life, it feels solid, continuous, stable. A table, a wall, even your own hands. They appear fixed and well-defined. But as physics has shown over the past century, this sense of solidity is more of an approximation than a fundamental truth. At smaller scales, matter becomes less certain, less concrete. Atoms, once thought to be the smallest indivisible units, are mostly empty space. A tiny nucleus surrounded by electrons that don't orbit in neat paths like planets, but instead exist as probability distributions, regions where they are more or less likely to be found, And if we go deeper still, into the nucleus, we find protons and neutrons made of quarks, held together by forces that are difficult to visualize in any classical sense. And eventually, we reach a point where our usual way of thinking begins to break down. Quantum mechanics describes this realm, and it does so with extraordinary precision. The equations work, the predictions match experiments with remarkable accuracy, and yet, the underlying picture it presents is unusual. Particles do not have definite positions until they are measured. They exist in superpositions, multiple possible states at once. Outcomes are not determined with certainty, but with probabilities. Now, the mainstream interpretation, often associated with what's called the Copenhagen interpretation, accepts this as a fundamental feature of reality. The universe, at its smallest scales, is inherently probabilistic. There is no deeper layer of hidden certainty, at least not one that we can access. But this interpretation, while widely taught, is not the only one. And this is where things begin to quietly open up again. Because some physicists have proposed that the apparent randomness of quantum mechanics might not be truly random at all, but instead reflect deeper processes that we do not yet understand. Hidden variable theories, for example, suggest that particles may have definite properties that are simply inaccessible to us. Others have explored the many worlds interpretation, where every possible outcome of a quantum event actually occurs, but in separate, branching universes. In this view, the universe is constantly splitting into multiple versions of itself, each representing a different possibility. Now, it's important to remain grounded here. These interpretations all reproduce the same observable results. They do not change the predictions of quantum mechanics. They only offer different ways of understanding what those predictions mean. And as of now, there is no experimental evidence that clearly favors one interpretation over another. So once again, we find ourselves in a familiar position. We have a theory that works extremely well, but whose deeper meaning remains open to interpretation. And that raises an interesting question. Is the uncertainty we see in quantum mechanics a feature of reality itself, or a reflection of the limits of our perspective? Because when we measure a quantum system, we interact with it. We become part of the process. The act of observation is not passive, it influences the outcome. This is sometimes referred to as the observer effect, though it's often misunderstood. It doesn't mean that consciousness directly creates reality, but it does mean that measurement, any interaction that extracts information, plays a fundamental role in determining what we observe. And this leads to a subtle but intriguing idea, that at the smallest scales, the universe may not be fully defined until it is observed or interacted with. Now again, the standard view treats this as a feature of quantum systems, not as a broader statement about reality as a whole. But it does invite a deeper consideration. Because if the act of observation plays a role in shaping what is observed, then the distinction between observer and system becomes less clear. And when you extend that idea, carefully, without jumping too far, it suggests that our understanding of the universe is not just about what is out there, but also about how we interact with it. And this becomes even more interesting when we consider something called quantum entanglement. When two particles become entangled, their properties become linked in such a way that measuring one instantly determines the state of the other, regardless of the distance between them. This has been experimentally verified many times, and it's one of the most well-established features of quantum mechanics. The mainstream explanation is precise. Entanglement does not allow for faster-than-light communication, and it does not violate relativity. Instead, it reflects a deeper kind of correlation between particles, one that does not depend on distance in the way we might expect. But the implications are still unusual, because it suggests that, at a fundamental level, the universe is not entirely separable. Things that appear distinct and distant may still be connected in ways that are not immediately visible. And if that's the case, then the idea of the universe as a collection of independent objects becomes less accurate. Instead, it begins to look more like a system of relationships, a network of interactions where the boundaries between parts are not always clearly defined. Now, this does not mean that everything is connected in some vague or mystical sense. The connections described by quantum mechanics are specific, measurable, and governed by precise rules. But they do challenge our intuition. They suggest that the way we perceive the world, divided into separate objects, each with its own independent properties, might be more of a practical framework than a fundamental one. And this brings us to something even more subtle, because if the smallest scales of the universe are governed by probabilities, interactions, and relationships rather than fixed properties, then the stability we observe at larger scales, the solidity of objects, the predictability of motion, must emerge from this underlying uncertainty. And indeed, this is what physics tells us. Classical behavior emerges from quantum systems when large numbers of particles interact. The randomness averages out and stable patterns appear. But this emergence is not always straightforward. It depends on conditions, interactions, and scale. And that means that the universe, at its core, may not be built from solid building blocks, but from something more dynamic, something that only appears solid when viewed from a certain perspective. So as you let this idea settle, consider how it connects to what we explored earlier. At the largest scales, we encounter limits to observation, boundaries beyond which we cannot see. At the smallest scales, we encounter limits to certainty, regions where properties are not fully defined until measured. In both cases, there is a kind of horizon, not just in space, but in understanding. And between these horizons lies everything we experience, the familiar world, the structured universe, the patterns we can observe and describe. But beyond them, things become less clear. Not chaotic, not unknowable in a dramatic sense, but simply less accessible. And perhaps that's the quiet thread running through all of this. That the universe is not just vast in size, but layered in a way that naturally limits what can be fully grasped. Not as a barrier, but as a feature. A system that reveals itself gradually, depending on where and how you look. And as we continue, we'll begin to explore how these layers might connect. How the largest structures and the smallest processes might not be separate at all, but part of the same underlying framework. A framework that, even now, we are only beginning to understand. As we continue, it becomes increasingly clear that the universe is not just a collection of separate ideas, large-scale structure, quantum behavior, expansion, unseen matter, but something more unified, even if that unity is not yet fully understood. And one of the most intriguing places where this sense of connection begins to emerge is in the concept of space-time itself. In everyday experience, space and time feel like two very different things. Space is where things exist. Time is what allows them to change. We move through space freely, but through time in only one direction. It feels natural, almost obvious. But according to modern physics, particularly Einstein's theory of general relativity, space and time are not separate. They are part of a single, interconnected framework known as space-time, a kind of four-dimensional fabric that can bend, stretch, and respond to the presence of matter and energy. Mass doesn't just exist in space-time, it shapes it. A planet like Earth curves the space-time around it, and that curvature is what we perceive as gravity. Objects follow paths within this curved geometry, not because they are being pulled in a traditional sense, but because they are moving along the natural contours of space-time itself. This is the mainstream explanation, and it has been confirmed through countless experiments and observations, from the bending of light around massive objects to the precise motion of planets, and even the recent detection of gravitational waves. And yet, Even here, where the theory is incredibly successful, there are deeper questions waiting just beneath the surface. Because if space-time can bend and stretch, then what is it made of? Is it something fundamental, like a kind of fabric that exists independently? Or is it something that emerges from deeper processes, something that only appears continuous at large scales, but is built from more basic components? Some approaches to quantum gravity suggest that space-time might not be smooth and continuous at the smallest scales. Instead, it could be discrete, made up of tiny units, almost like pixels in a digital image, but far smaller than anything we can currently detect. If this is true, then what we experience as a smooth flow of space and time could be an approximation, an emergent property of something more granular underneath. And that idea, while still speculative, opens up a very interesting line of thought, because it suggests that space-time itself, the stage on which everything happens, might not be fundamental. It might be something that arises from deeper relationships. Now, one of the more intriguing developments in theoretical physics over the past few decades involves the idea that space-time could be connected to information, not in a metaphorical sense, but in a very precise, mathematical way. For example, in certain models of black holes, the information about everything that falls into them appears to be encoded on their surface, on what's called the event horizon. This has led to the development of the holographic principle, which suggests that the information contained within a volume of space might be fully described by data on its boundary. In simple terms, it's like saying that a three-dimensional region could be represented by a two-dimensional surface. Now, this is still an area of active research, and it's not something that has been fully confirmed in all contexts. But it is taken seriously because it emerges naturally from attempts to reconcile quantum mechanics with gravity. And if it's even partially correct, it suggests something quite profound. That the universe at a fundamental level might be less about objects moving through space, and more about information being processed and structured in certain ways. Again, it's important to stay grounded here. This does not mean the universe is a simulation, or that reality is just information in a simplistic sense. But it does point toward a shift in perspective. Instead of thinking of space, time, and matter as the primary ingredients of reality, we might begin to think in terms of relationships, interactions, and encoded structures. And this begins to connect back to what we explored earlier. The idea that, at the smallest scales, properties are not fixed until measured. The idea that at the largest scales, there are limits to what can be observed. And now, the idea that the very framework in which all of this occurs, space-time, might itself be something that emerges from deeper rules. So rather than imagining the universe as a solid, fully defined system, it starts to feel more like a layered process, a system where what we see depends on the scale at which we observe. At large scales, we see galaxies, clusters, and cosmic structure. At smaller scales, we see particles, probabilities, and interactions. And beneath both, there may be something more abstract, something that gives rise to both structure and uncertainty. Now, there are also alternative approaches that question whether space-time should be treated this way at all. Some theories suggest that gravity itself might not be a fundamental force, but an emergent phenomenon, something that arises from statistical behavior at microscopic levels, much like temperature emerges from the motion of particles. Others explore the possibility that space-time is not continuous across the entire universe, but could have different properties in different regions or under extreme conditions. These ideas are still being explored, tested, refined, but they all share a common theme, that what we perceive as the basic structure of reality might not be the deepest layer. And that raises a subtle but important question. If space-time is not fundamental, then what is? What is the underlying framework from which space, time, matter, and energy all emerge. At this point, we don't have a definitive answer, but we do have clues. Patterns in the equations, connections between seemingly unrelated areas of physics, hints that point toward a deeper level of organization. And perhaps more importantly, we have a growing recognition that our current categories, space, time, particle, force, may be approximations. Useful, accurate within certain domains, but not necessarily final. So as you continue to listen, let this idea settle in a quiet, unhurried way, that the universe might not be built from things, but from processes, not from static objects, but from relationships that give rise to what we experience as objects, and that what we call reality might be something that becomes more defined the closer we look, and more abstract the deeper we go. And as we move forward, we'll begin to explore how this connects to one of the most intriguing aspects of the universe, the nature of time itself, not just as something that passes, but as something that might not behave the way we intuitively expect. Because if space can bend, if matter can be uncertain, and if observation plays a role in defining outcomes, then time too may have layers we haven't fully uncovered. As we continue, we arrive at something that feels familiar, almost ordinary, and yet becomes increasingly difficult to define the more closely we examine it. Time. It's something we experience constantly. You can feel it passing even now, moment to moment, steady, unbroken, always moving forward. It gives structure to everything. Cause leads to effect. Past becomes present, present becomes future. It feels linear, reliable, almost absolute. But when physics takes a closer look at time, that sense of simplicity begins to soften. According to relativity, time is not the same everywhere. It can stretch, slow down, even differ, depending on motion and gravity. Clocks on satellites tick slightly faster than clocks on Earth. Time passes more slowly near massive objects. These effects are not theoretical. They are measured, accounted for, built into systems like GPS. So already, time is not a universal constant. It is flexible, dependent on context. And yet, even with that understanding, we still tend to think of time as something that flows from past to future in a single direction. But here's where it becomes more subtle. The fundamental equations of physics, those that describe the motion of particles, the behavior of forces, do not strongly prefer a direction of time. In many cases, they work just as well forward as backward. If you were to watch certain physical processes in reverse, the equations would still hold. And this creates a quiet tension, because our experience of time is clearly directional. We remember the past, not the future. Causes come before effects. Entropy, often described as disorder, tends to increase over time. This directional flow is sometimes called the arrow of time, and it is closely associated with the second law of thermodynamics, which states that in an isolated system, entropy tends to increase. The mainstream explanation is that the universe began in a very low entropy state, highly ordered, and has been evolving toward higher entropy ever since. This progression gives rise to the sense of time moving forward. But this explanation, while widely accepted, leads to a deeper question. Why did the universe begin in such a low entropy state? Because statistically, high entropy states are far more likely. So the fact that the universe started in a highly ordered condition is unusual. Not impossible, but not something that is fully explained by current models. And once again, we find ourselves at a familiar boundary. We have a framework that works, thermodynamics, statistical mechanics, but at its foundation lies an initial condition that remains somewhat mysterious. And this opens the door to careful speculation, not as a replacement for the standard model, but as an exploration of its edges. Some physicists have proposed that time's arrow might not be fundamental, but emergent, arising from boundary conditions or statistical behavior, rather than being built into the laws themselves. Others have suggested that time might not flow in a single direction at all, but that what we perceive as forward motion is tied to how information is processed and stored. There are even models where time could be symmetrical, flowing outward in both directions from a central point, with what we call the past and future being relative to our position within that structure. Now, these ideas are still highly theoretical, and many remain difficult to test, but they arise from real attempts to reconcile the behavior of time with the underlying symmetry of physical laws. And they all point to the same quiet realization. That time, as we experience it, may not be as straightforward as it seems. Because if the laws of physics do not strongly distinguish between past and future, then the direction we experience might be tied to something else. Something about how systems evolve, how information accumulates, how memory works. And that leads to an interesting intersection between physics and perception. Because our experience of time is deeply connected to how we process information. We remember the past because information about it is stored in our brains, in records, in physical states. The future, by contrast, has not yet left such traces. So from our perspective, the past feels fixed and the future feels open. But at a deeper level, the distinction may not be as absolute. Now it's important to remain grounded here. There is no evidence that we can move freely through time, or that the future already exists in a way we can access. But the structure of physical laws does leave room for interpretation, and that's where things become quietly intriguing. Because it suggests that time might not be a single, universal river flowing in one direction, but something more layered, something that depends on scale, context, and perspective. At the human level, time feels continuous and directional. At the relativistic level, it bends and stretches. At the quantum level, its role becomes even less clear, sometimes appearing as a parameter rather than a fundamental entity. And in some theoretical models, time might not even exist in the way we think. It could emerge from more basic relationships, much like space-time itself. So as you let this idea settle, consider how it connects to everything we've explored so far. The limits of observation at large scales, the uncertainty at small scales, the possibility that space-time itself is emergent, and now the idea that time, one of the most familiar aspects of experience, may also be part of that deeper structure. Not fixed, not absolute, but something that arises under certain conditions. And if that's the case, then the universe becomes something even more subtle. Not just a place where things happen over time, but a system where time itself is part of what is happening. A feature, not a background. And as we continue, we'll begin to explore how these ideas come together when we consider one of the most extreme environments in the universe. Places where gravity, time, and quantum effects all interact in ways that challenge our current understanding. Places where the boundaries we've been discussing become more than theoretical. They become real, measurable, and still not fully understood. As we continue, we move towards some of the most extreme and revealing environments in the universe, places where many of the ideas we've been exploring begin to overlap, sometimes in ways that feel almost contradictory. These are regions where gravity becomes so intense, space-time so distorted, and our current theories so stretched that the boundaries of understanding become especially clear. Black holes. At a distance, they seem almost simple. A region of space where gravity is so strong that nothing, not even light, can escape. They form when massive stars collapse under their own gravity, compressing matter into an incredibly dense state. Surrounding each black hole is a boundary known as the event horizon, the point beyond which escape is no longer possible. This is the mainstream picture, supported by decades of observation and, more recently, even direct imaging of black hole shadows. And yet, as we look closer, black holes begin to reveal something deeper. Because they are not just objects. They are, in many ways, intersections, places where general relativity and quantum mechanics meet. And when those two frameworks meet, things become less clear. According to general relativity, if you fall into a black hole, you would pass through the event horizon without noticing anything particularly special at that exact moment. From your perspective, time would continue as usual, at least initially. But as you move closer to the center, tidal forces would increase dramatically, eventually stretching and compressing you in a process sometimes referred to as spaghettification. From the outside, however, things appear very different. An observer watching you fall in would never actually see you cross the event horizon. Instead, you would appear to slow down, becoming dimmer and more red-shifted, gradually fading from view. So already, we have two valid descriptions of the same event, one from the falling observer, one from the distant observer, and they don't quite align in an intuitive way. Both are correct within their respective frames of reference. But when you try to combine them into a single, unified picture, it becomes more complicated. And this is just the beginning. Because when quantum mechanics is introduced into the picture, a new layer of questions emerges. In the 1970s, physicist Stephen Hawking showed that black holes are not completely black. Due to quantum effects near the event horizon, they can emit radiation, now known as Hawking radiation, and slowly lose mass over time. This leads to a surprising conclusion. Black holes can eventually evaporate. Now, this is where things become especially interesting. Because if a black hole evaporates completely, what happens to the information about everything that fell into it? In quantum mechanics, information is not supposed to be destroyed. The evolution of a system is reversible at a fundamental level. But if matter falls into a black hole, and the black hole disappears, it seems like that information is lost. This is known as the black hole information paradox, and it remains one of the most significant unresolved questions in theoretical physics. The mainstream view is that information is not truly lost, that it must somehow be preserved, perhaps encoded in subtle correlations within the Hawking radiation, or stored on the event horizon itself. This idea connects back to the holographic principle we mentioned earlier, the possibility that information about a volume of space can be represented on its boundary. But the exact mechanism is still being worked out, and in the process, new ideas have emerged. Some researchers have proposed that the event horizon might not be as smooth as general relativity suggests. Instead, it could be a more dynamic, complex region, sometimes described in speculative terms as a firewall, though this idea is still debated. Others have explored the possibility that black holes could be connected to other regions of space-time through structures known as wormholes. Now, wormholes are solutions to the equations of general relativity, but whether they exist in reality and whether they could be stable is still uncertain. But the fact that such solutions exist at all is intriguing, because it suggests that space-time, under certain conditions, might allow for connections that go beyond our usual understanding of distance and separation. Again, this is not evidence that wormholes are real in a practical sense, but it does highlight how, at the extremes, our current frameworks begin to open up into a wider space of possibilities, and black holes seem to sit right at that edge. They are not just astrophysical objects, but theoretical laboratories, places where the limits of our understanding are tested. Because inside a black hole, according to general relativity, lies a singularity, a point of infinite density where the known laws of physics break down. And just like with the Big Bang, this singularity is less of an answer and more of a signal, a sign that our current theories are incomplete, that something deeper is needed to fully describe what's happening. So when we look at black holes, we're not just observing distant objects in space. We're looking at boundaries, places where time behaves differently, where information becomes a central question, where space-time itself may be pushed to its limits. And in those places, the universe reveals something subtle, that the frameworks we use, relativity, quantum mechanics, are incredibly powerful, but not yet fully unified. They work extremely well in their respective domains, but when combined, they leave questions. Not contradictions, exactly, but gaps. And those gaps are where much of modern theoretical physics is focused, trying to understand how these pieces fit together, trying to find a deeper framework that can describe both the large-scale structure of space-time and the small-scale behavior of quantum systems. And as we consider all of this, it brings us back to a familiar theme, that the universe is layered. At everyday scales, it feels stable and predictable. At cosmic scales, it reveals structure and expansion. At quantum scales, it becomes probabilistic. And at the extremes, inside black holes, at the beginning of the universe, it becomes something we are still trying to fully describe. And perhaps that's part of what makes black holes so compelling. They are not just objects to be studied. They are questions, physical manifestations of the limits of our current understanding. And as you let that settle in, as the idea of these distant, silent regions of space-time begins to feel less abstract and more present, consider this. The universe may not hide its deepest secrets. It may simply place them at the boundaries, at the edges where our current knowledge begins to fade. And as we continue, we'll begin to explore another one of those edges, one that connects not just physics, but the very nature of observation and reality itself. Because when we start to ask how the universe is observed and what it means to observe at all, we begin to approach a question that is both scientific and deeply subtle. A question about the role of the observer. As we continue, the focus shifts slightly, not away from the universe itself, but towards something that is always present within it, yet often overlooked in discussions of cosmology and physics. The observer. Up to now, we've explored vast structures, unseen matter, quantum uncertainty, space-time, and black holes. And in each of these, there has been an implicit assumption that there is something observing, measuring, interpreting. But what exactly does that mean? In classical physics, the role of the observer is straightforward. Systems exist in well-defined states, and measurements simply reveal those states. The observer does not fundamentally alter the system being observed. There is a clear separation between the two. But as we saw earlier with quantum mechanics, that separation begins to blur. At the quantum level, observation is not passive. It plays a role in determining outcomes. A particle does not have a definite position until it is measured. A system exists in multiple possible states, and the act of measurement selects one of those possibilities. Now, the mainstream interpretation handles this carefully. It does not require consciousness or intention. Any interaction that extracts information can count as a measurement. A detector, a photon, an environment, these are sufficient. But even with that clarification, something remains quietly unusual, because it means that the properties we observe are not always fixed independently of observation. They are, in some sense, relational, defined through interaction. And this introduces a subtle shift in how we think about reality. Instead of imagining a universe made of objects with intrinsic independent properties, we begin to consider a universe where properties arise through relationships, through interactions between systems. Now, this idea has been developed further in certain interpretations of quantum mechanics, sometimes referred to as relational quantum mechanics. In this view, the state of a system is not absolute, but relative to the observer or the system interacting with it. So what is real can depend on perspective, not in a subjective or arbitrary way, but in a structured, consistent way, defined by interactions. And again, it's important to stay grounded. This does not mean reality is an illusion or that anything can be anything. It means that at the deepest levels, the universe may be less about isolated things and more about connections. Now, when we step back and connect this idea to the larger picture, something interesting begins to emerge. Because earlier, we talked about how space-time might be emergent, arising from deeper relationships. We talked about how quantum systems are defined by probabilities and interactions. And now, we're considering the possibility that even the properties of systems are not fixed until they are observed or interact. So there is a pattern forming, a consistent shift away from thinking in terms of independent objects, and toward thinking in terms of networks of relationships. And within that network, the observer is not separate. The observer is part of the system. Now, this becomes particularly intriguing when we consider the universe as a whole, because if everything within the universe is part of this network of relationships, then any observation is also part of the universe observing itself. Not in a metaphorical sense, but in a literal one. We are made of the same particles, governed by the same laws, embedded within the same space-time. So when we observe the universe, we are not stepping outside of it. We are participating in it. And this creates a kind of loop. The universe, through us, examining its own structure. Now, the standard scientific approach does not treat this as something mystical. It is simply a recognition that observers are physical systems within the universe. But when you consider it more slowly, more carefully, it does introduce an interesting perspective, because it suggests that knowledge of the universe is always internal. There is no external viewpoint, no place from which the entire system can be observed from the outside. Every measurement, every observation, every theory, these are all constructed from within. And that means that our understanding of the universe is always shaped by our position within it. Not in a limiting sense necessarily, but in a contextual one. Now, this idea connects to something we touched on earlier, the limits of observation. We cannot see beyond the observable universe. We cannot access regions beyond the cosmic horizon. And now, we can add another layer. We cannot step outside the system to observe it as a whole. We are always inside. And that may influence not just what we can observe, but how we interpret what we observe. Because our theories are built from data, and our data is shaped by interactions, and those interactions are part of the system we are trying to understand. So once again, we encounter a boundary. Not a physical one this time, but a conceptual one. A limit to perspective. And within that limit, there is still enormous room for discovery. Because even though we cannot step outside the universe, we can explore its internal consistency. We can look for patterns, test predictions, refine models. And that's exactly what science does. But at the same time, it's worth holding on to the awareness that our picture of the universe is always a view from within. And that perspective may carry with it certain assumptions, certain structures that feel natural to us because of how we experience reality. Now, some researchers have explored whether consciousness itself plays a deeper role in this picture. This is a more speculative area, and it's important to approach it carefully. There is currently no scientific consensus that consciousness has a direct effect on physical reality in the way sometimes suggested in popular discussions. Most interpretations of quantum mechanics do not require consciousness as a fundamental component. However, the relationship between consciousness and physical systems, how subjective experience arises from physical processes, is still not fully understood. And so, while it may not directly shape quantum outcomes, it remains an open question in a different sense. How does the universe give rise to observers capable of reflecting on the universe? How does a system become aware of itself? These are questions that extend beyond physics into neuroscience, philosophy, and information theory. But they connect back to the same theme: that the universe is not just a collection of objects, but a system capable of generating structure, interaction, and eventually, awareness. And as we sit with that idea, quietly, without rushing to conclusions, it becomes less about finding a final answer and more about recognizing the depth of the question itself. Because when we look at the universe, we are not just looking outward, we are also, in a way, looking inward, exploring the conditions that allow observation to happen at all. And as we continue, we'll begin to explore how all of these threads, space, time, matter, observation, might come together in one of the most intriguing possibilities currently being considered. The idea that the universe, at its deepest level, might be governed not just by physical laws, but by underlying principles of information, computation, or structure that we are only beginning to glimpse, not as a conclusion, but as the next question. As we continue, the threads we've been gently following, space-time, quantum behavior, observation, structure, begin to converge toward a quieter but increasingly discussed idea. Not one that replaces physics, but one that tries to sit beneath it, offering a different way of describing what might be happening at the deepest level. The idea that the universe may, in some sense, be fundamentally connected to information. Now, to be clear from the beginning, this does not mean the universe is literally a computer in the everyday sense, or that reality is simply a digital simulation. Those are interpretations that extend far beyond what current science can confirm. But within physics itself, there has been a growing recognition that information plays a central, unavoidable role. We've already seen hints of this. In quantum mechanics, the state of a system is described in terms of probabilities, information about what could be observed. Measurement updates that information. In black hole physics, the question of what happens to information has become one of the most important unresolved problems. And in the holographic principle, the idea emerges that information about a volume of space might be encoded on its boundary. These are not fringe ideas. They arise directly from attempts to make existing theories consistent. And taken together, they suggest something subtle. That information is not just a tool we use to describe the universe, but may be part of its underlying structure. Now, the mainstream interpretation treats information in a precise way. It is defined mathematically, measured in bits, and used to describe states, correlations, and entropy. It is not abstract in the philosophical sense. It is quantifiable, testable, embedded in physical systems. But even within that framework, there is an interesting shift. Because traditionally, physics has focused on things, particles, fields, forces. And now, increasingly, it also focuses on relationships, correlations between systems, the flow of information between states. And this shift becomes especially noticeable in quantum theory. For example, when two particles are entangled, what is fundamentally shared between them is not a physical substance, but information about their joint state. The correlation exists even when the particles are separated by vast distances. So what is real in that situation? Is it the particles themselves, or the relationship between them? The mainstream answer is that both are part of the full description. But the emphasis on relationships has led some researchers to explore whether information might be more fundamental than the objects it describes. And this leads to a careful but intriguing possibility that what we perceive as physical reality, space, time, matter, might emerge from deeper informational structures. Again, this is not a proven theory, but it is being explored in several areas of theoretical physics, including quantum gravity and certain approaches to unifying physics. And it connects to something we touched on earlier, the idea that space-time itself might be emergent. If space-time can arise from more basic processes, then what are those processes made of? Some models suggest they could be networks of information, connections, interactions, relationships that, when viewed at larger scales, appear as geometry. In this view, space is not a backdrop in which things exist. It is something that emerges from how information is connected. Now, this may sound abstract, but there are concrete mathematical frameworks being developed to explore it. For example, certain models use networks or graphs where the connections between nodes represent relationships, and the structure of those connections gives rise to something that behaves like space. Similarly, time might emerge from the ordering of events, the way information changes or updates, rather than existing as a separate, flowing dimension. So instead of thinking of the universe as something that exists in space and time, we might begin to think of space and time as something that emerges from the way the universe is structured at a deeper level. Now, it's important to remain cautious. These ideas are still under development. They are not yet confirmed, and they may evolve or be replaced as new evidence emerges. But they do provide a different lens, one that shifts the focus from objects to structure, from things to relationships. And when you step back and look at everything we've explored so far, this lens begins to tie things together in an interesting way. The uncertainty of quantum mechanics becomes a feature of how information is distributed and updated. The structure of the cosmic web becomes a large-scale manifestation of underlying connections. The limits of observation become limits on accessible information. Black holes become systems where information is compressed, transformed, and possibly redistributed. And the role of the observer becomes part of how information is extracted and defined. So instead of seeing these as separate phenomena, they begin to look like different expressions of the same underlying principle. Now again, this is not a final answer. It is a direction of exploration. But it raises a question that is both simple and surprisingly deep. If the universe is, at some level, about information, then what determines the rules by which that information behaves? Why does it organize itself into the patterns we observe? Why do certain structures emerge, atoms, stars, galaxies, observers, while others do not? These are questions that move us slightly beyond physics as it is traditionally practiced, and towards something more foundational, not in a mystical sense, but in a structural one. Trying to understand not just how the universe behaves, but why it has the structure it does. And as we sit with that idea, slowly, without rushing to conclusions, it becomes clear that we are approaching a different kind of boundary, not a boundary of observation or of scale, but of explanation. A point where our current frameworks begin to describe patterns very well, but do not yet fully explain why those patterns exist in the form they do. And within that space, there is still room for careful, grounded curiosity. Because even if we don't yet have all the answers, we can begin to notice the connections. We can see how different areas of physics point towards similar underlying themes, and we can follow those themes a little further. So as you continue to listen, let this idea settle in a quiet, open way, that the universe may not just be made of matter and energy, but of structure and relationships, that what we perceive as reality might be one layer of a deeper system, one that we are only beginning to describe, and that somewhere within that system, there may be principles that tie everything together, not hidden, not unreachable, just not fully understood yet. And as we continue, we'll begin to explore one more layer, how all of these ideas might connect to the question of whether the universe is finite or infinite, and what that distinction really means when examined closely. Because even something as simple as how big is the universe becomes far more subtle the deeper you look. As we continue, the question we arrive at feels almost simple on the surface, but becomes increasingly subtle the more carefully we examine it. How big is the universe? At first, the answer seems straightforward. We've mapped the observable universe, measured its expansion, estimated its age, we can say that the observable portion extends roughly 46 billion light-years in every direction. That's the region from which light has had time to reach us since the beginning of cosmic expansion. But as we've already touched on, the observable universe is not necessarily the entire universe. It's just the part we can see. And that distinction between what is observable and what exists turns out to be more important than it first appears. Because when cosmologists study the geometry of the universe, they often describe it in terms of curvature. If the universe has positive curvature, like the surface of a sphere, then it would be finite, but without edges. You could travel in one direction and eventually return to your starting point. If it has zero curvature, it would be flat, extending infinitely in all directions. If it has negative curvature, it would be open and also likely infinite, but with a different kind of geometric structure. Now, based on current measurements, particularly of the cosmic microwave background, the universe appears to be very close to flat. And this leads to the mainstream conclusion that the universe is either infinite or so large that its curvature is too small for us to detect. But here's where things begin to open up again, because flat does not automatically mean infinite. It means that, within the limits of our observation, the geometry does not show curvature. But beyond those limits, we don't know. The universe could still be finite, just on a scale far larger than what we can observe. Or it could be infinite. And if it is infinite, that introduces a set of ideas that are both mathematically consistent and conceptually difficult to fully grasp. Because in an infinite universe, certain possibilities become not just likely, but inevitable. Given enough space, even extremely rare configurations of matter should occur somewhere. Entire regions of the universe could exist that are nearly identical to our own. Same structures, same physical laws, perhaps even similar histories. Now, to be clear, this is not something we can observe or confirm. It's a consequence of extrapolating known physics into an infinite framework. But it raises an interesting point, because it suggests that the structure of the universe, finite or infinite, has implications not just for size, but for possibility. In a finite universe, there is a limit to how much can exist. In an infinite one, the limits are different. Now, the mainstream approach remains cautious. Cosmologists focus on what can be measured, what can be tested. The question of true infinity is often treated as a boundary condition, something that emerges from models but is difficult to verify directly. And yet, it remains an open question, because we simply do not have access to the full extent of the universe. And that brings us back to something we've encountered several times already. The idea that our understanding is shaped by what we can observe. We measure curvature within the observable universe. We model expansion based on available data. And from that, we infer larger structures. But those inferences, while grounded, are still extrapolations. And this leads to a subtle but important realization that when we ask, is the universe infinite, we are really asking a question that may not have a fully observable answer. Not because it's unimportant, but because it lies beyond the horizon of what we can directly test. Now, there are also alternative ways of thinking about this. Some models suggest that the universe might be finite, but unbounded, like the surface of a sphere, but in higher dimensions. Others explore the possibility that what we call the universe might be just one region within a larger structure, perhaps part of a multiverse, where different regions have different properties. These ideas arise from extensions of inflationary theory and other frameworks. But again, they remain speculative, not in the sense of being unfounded, but in the sense of being not yet confirmed. And so we find ourselves once again in that familiar space. A core of well-supported knowledge, surrounded by possibilities. Now, there is another layer to this question that is often overlooked. Because when we think about the size of the universe, we tend to imagine it as something that exists within a larger space, something that expands into something else. But according to general relativity, that's not quite accurate. The universe is not expanding into pre-existing space. Space itself is expanding. So when we ask, how big is the universe? We're not measuring it against an external backdrop. We're describing the internal structure of space-time itself. And that can be difficult to visualize, because it means there is no outside in the usual sense. No edge where the universe ends and something else begins. Instead, the universe contains all of space, at least as far as our current models describe. And that shifts the question slightly, because instead of asking how big the universe is in relation to something else, we are asking about the extent of the system itself, a system that may or may not be bounded. Now, if we connect this back to everything we've explored so far, something interesting begins to take shape. The limits of observation define what we can see. The structure of space-time defines how distances behave. The role of information defines how systems are described. And now, the question of size becomes tied to all of these. Because the size of the universe is not just about distance, it's about what can exist, what can be observed, and how those two relate. And within that, there is still uncertainty. Not a lack of knowledge, but an openness. A recognition that some aspects of the universe may remain beyond direct confirmation. And perhaps that's part of what makes this question so compelling, because it sits right at the edge of what we can know, not just technically, but conceptually. And as you let that idea settle gently, without needing to resolve it, consider this. The universe may be finite. It may be infinite. It may be far larger than anything we can observe, or it may have structures that we have not yet imagined. But whatever the case, our understanding of it will always begin from within. From this small region, this observable window, this place where we can measure, think, and explore. And from here, we extend outward, not with certainty, but with curiosity. And as we continue, we'll begin to bring these ideas together, not to conclude, but to reflect, to look at the patterns that have emerged across everything we've explored, and consider what they might suggest about the nature of the universe as a whole. As we continue, something subtle begins to happen. After moving through scale, from the largest observable structures to the smallest quantum interactions, from space-time to information, from time itself to the limits of observation, we start to notice that the same kinds of patterns appear again and again. Not identical patterns, not something simple or repetitive, but echoes. At the largest scales, the universe organizes into a cosmic web, filaments, clusters, voids. At smaller scales, matter organizes into atoms, molecules, and complex systems. At even smaller scales, interactions are governed by probabilities, relationships, and exchanges of information. Different levels, but similar underlying themes. Structure emerging from simplicity, order arising from interaction, complexity building from relatively simple rules. And this raises a quiet question. Are these patterns just coincidences, independent results of different processes operating at different scales? Or are they reflections of something more fundamental, something that operates across all levels of the universe? Now, the mainstream scientific view tends to approach each scale with its own framework. Cosmology describes large-scale structure. Quantum mechanics describes small-scale behavior. Thermodynamics describes statistical systems. Each works extremely well within its domain. But one of the long-term goals of physics has always been unification. To find a framework that connects these domains, not just mathematically, but conceptually. And while we haven't yet achieved a complete unification, there are hints that such connections may exist. For example, The mathematics used to describe certain quantum systems has unexpected similarities to the mathematics used in gravitational theories. Concepts from information theory appear in black hole physics. Ideas about entropy connect thermodynamics, cosmology, and quantum mechanics. These are not isolated coincidences. They suggest that different areas of physics may be describing different aspects of the same underlying structure. Now, it's important to remain careful here. These connections do not yet form a complete theory. They are clues, but they are consistent enough to be taken seriously. And when you step back and look at them together, they begin to suggest a different way of thinking about the universe. Not as a collection of separate systems, but as a single, layered process. A system where different levels of description, classical, quantum, relativistic, are not competing explanations, but complementary perspectives, each one capturing part of the whole. And this brings us to a subtle but important shift, because instead of asking, which theory is correct, we begin to ask, how do these theories fit together? What is the deeper framework that allows all of them to be valid in their respective domains? Now, one approach to this question involves looking for principles that remain consistent across scales. For instance, conservation laws, energy, momentum, charge, appear in many areas of physics. Symmetry principles play a central role in both quantum theory and relativity. And information, as we discussed earlier, appears in multiple contexts. So rather than focusing on specific objects or forces, we might begin to focus on these underlying principles, the rules that govern how systems behave, regardless of scale. And this leads to a quiet but intriguing possibility, that the universe, at its deepest level, may be defined not by what it contains, but by how it operates, by the rules that determine how structure forms, how systems evolve, how information is processed. Now, this idea is still being explored, and it does not replace the need for detailed physical models. But it does provide a different perspective, one that emphasizes relationships, patterns, and consistency across different levels of description. And when you combine this with everything we've explored so far, a kind of picture begins to emerge. Not a complete picture, not a final answer, but a direction, a sense that the universe may be more unified than it first appears. That the boundaries between different areas of physics may not be fundamental, but reflective of how we categorize and study different aspects of the same system. And this brings us to something even more subtle, because if the universe is a unified system, and if our understanding of it is built from within that system, then our theories are not just descriptions of the universe. They are part of the universe. They are structures, patterns of information that exist within the same framework they describe. And that creates an interesting kind of recursion. The universe producing observers, observers producing theories, theories describing the universe. A loop, not in a circular or self-contradictory sense, but in a layered one. Each level building on the previous, each one refining the next. Now, again, this is not something that changes the predictive power of physics. It's a perspective, a way of understanding the relationship between knowledge and reality. And within that perspective, something becomes clear, that the process of understanding the universe is itself part of the universe's structure, not separate from it. And that means that the limits we've been discussing, the limits of observation, of scale, of perspective, are not obstacles to be overcome entirely. They are features of the system, boundaries that shape how knowledge develops. And perhaps that's part of what makes this exploration feel the way it does. Not like solving a puzzle with a final answer, but like gradually revealing a pattern that becomes clearer the more carefully you look. A pattern that doesn't end, but deepens. So as you continue to listen, as these ideas settle into a quieter rhythm, consider this. The universe may not be something that can be fully captured in a single model or theory. Not because it is disordered or chaotic, but because it is layered. Because it can be described in different ways at different scales, each one revealing something real, but not complete on its own. And within that layering, there is coherence, a consistency that allows all these perspectives to fit together, even if we don't yet fully understand how. And as we move forward, we'll begin to explore one final idea that sits quietly beneath all of this. Not a theory, not a model, but a question. A question about whether the universe, in all its complexity, might be constrained, not just by physical laws, but by something even more fundamental. Something that determines not just how the universe behaves, but what is possible within it at all. As we continue, we move into a space that feels quieter, not because it contains less, but because it sits beneath everything we've already explored. A layer that isn't tied to any one theory or scale, but instead touches all of them at once. A simple question, but one that becomes increasingly difficult the longer you sit with it. Why does the universe follow the rules that it does? Up to now, we've been describing how the universe behaves. We've talked about gravity shaping space-time, quantum mechanics governing probabilities, thermodynamics guiding the flow of entropy. These are the laws, the frameworks that allow us to make predictions, to understand patterns, to connect observations, and they work with remarkable precision. But there's a quiet distinction here that often goes unnoticed. Describing how something behaves is not the same as explaining why it behaves that way. Physics, at its core, is extraordinarily good at the first part. It identifies patterns, formulates laws, tests predictions. But when we ask why those laws exist in the form they do, the question becomes more subtle, because any explanation we give tends to rely on deeper laws. And those deeper laws raise the same question again. Why those? So as we follow this line of thinking carefully, we find ourselves moving toward a kind of foundation, not necessarily a final answer, but a boundary where explanation begins to shift. Some physicists approach this by looking for a theory of everything, a single framework that unifies all forces, all particles, all interactions, something from which the known laws emerge as specific cases. This is an active area of research. String theory, loop quantum gravity, and other approaches attempt to move in this direction. But even if such a theory were found, even if it perfectly described all known phenomena, it would still leave a question. Why that theory? Why those underlying rules instead of others? Now, the mainstream scientific approach often stops here, not because the question is unimportant, but because it may lie outside the scope of what can be tested. Science focuses on models that can be observed, measured, falsified, and questions about why the laws themselves exist in a particular form may not always produce testable predictions. But that doesn't make the question meaningless. It simply places it at a different level. A level where physics begins to intersect with philosophy, mathematics, and even logic. Some have suggested that the laws of the universe might be the only consistent ones possible, that any other set of rules would lead to instability, contradiction, or a universe that cannot sustain structure. In this view, the universe is the way it is because it has to be, not by design, but by necessity. Others explore the idea that there could be many possible sets of laws realized in different regions of a larger multiverse. In that case, we find ourselves in a universe with laws that allow for observers, not because those laws are unique, but because they are compatible with our existence. Again, this is a form of selection, not intention. And still others consider whether the laws of physics might themselves evolve, whether they are not fixed, but emerge over time, shaped by deeper processes. Now, these ideas are still speculative, but they all arise from the same underlying question. Not how the universe behaves, but why it behaves in a way that allows for structure, complexity, and stability at all. And as we sit with that, something interesting begins to happen, because the question starts to shift slightly. From why these laws to what makes any law possible. What allows the universe to be described in terms of consistent patterns? Why is there order rather than complete randomness? Because if the universe were entirely random, if there were no consistent relationships, no repeatable patterns, then physics as we know it would not be possible. There would be nothing to describe, no stable structures, no predictable behavior. And yet, what we observe is the opposite. A universe with remarkable consistency, laws that apply across vast distances and timescales, patterns that can be expressed mathematically with extraordinary precision. And that leads to a quiet but profound realization that the universe is not just something that exists, but something that is structured in a way that allows it to be understood. Now again, this does not imply intention or design. It simply highlights a property, that the universe is, in some sense, intelligible. And that intelligibility is what makes science possible. But it also raises a deeper curiosity, because intelligibility itself is not something we fully explain. We observe it, we rely on it, but why it exists remains open. Now, if we connect this back to everything we've explored, the limits of observation, the emergence of space-time, the role of information, the layered nature of reality, we begin to see that this question sits beneath all of it. It is not about any one phenomenon. It is about the framework that allows all phenomena to exist in a coherent way. And perhaps that's why it feels different, quieter, less about specific answers and more about the structure of explanation itself. So as you continue to listen, let this idea settle without needing to resolve it. That the universe may not just be governed by laws, but by principles that determine what kinds of laws are possible. That beneath the patterns we observe, there may be a deeper level of consistency. Not something hidden, but something so fundamental that we often take it for granted. And that as we explore further, we are not just uncovering facts about the universe, we are gradually encountering the conditions that make those facts possible in the first place. And from here, we begin to move towards something that feels less like a question of physics alone, and more like a reflection, a quiet consideration of what all of this suggests when taken together. Not as a conclusion, but as a way of seeing the universe a little differently. As we continue, the pace naturally begins to slow, not because there is less to explore, but because the ideas themselves begin to feel more integrated, less like separate questions and more like parts of a larger pattern that has been gradually coming into view. Up to this point, we've moved through many layers of the universe. We've looked outward to its largest structures and inward to its smallest scales. We've considered space-time, quantum uncertainty, black holes, information, observation, and the nature of physical laws. And each time, we've encountered something similar, a boundary. Not a hard edge, but a place where understanding becomes less certain and more open. And now, instead of introducing something entirely new, it becomes more useful to gently bring these threads together, to notice what they suggest when seen as part of the same picture. Because when you step back, something quietly consistent appears. At every level, the universe seems to balance between structure and uncertainty. At large scales, we see galaxies arranged in patterns, but shaped by processes we don't fully control or observe in real time. At small scales, we see probabilities instead of certainties, but those probabilities follow precise mathematical rules. Space-time behaves like a continuous fabric, but may emerge from something more discrete. Time feels directional, but arises from conditions that may not themselves have a direction. Information appears fundamental, but we don't yet fully understand why it behaves the way it does. And so, across all these domains, there is a kind of tension, not a contradiction, but a balance between what is defined and what is not fully defined, between what can be measured and what can only be inferred. And this balance might not be a limitation, it might be a feature, because if everything were completely fixed, completely determined at all levels, there would be no room for variation, no emergence of complexity, no unfolding of structure over time. And if everything were completely random, with no consistent rules, there would be no stability, no patterns, no way to describe or understand anything at all. But what we observe is something in between. A universe that follows rules, but allows for variation. A system that is structured, but not rigid. And within that balance, complexity becomes possible. Stars form, galaxies evolve, chemical structures emerge. Eventually, systems capable of observing and reflecting appear. And that progression, from simple to complex, is not something that was explicitly programmed into the laws of physics, at least not in any obvious way. It emerges from interactions, from conditions, from the interplay between order and flexibility. Now, the mainstream scientific view explains much of this in terms of known processes: gravity, thermodynamics, chemistry, evolution. These frameworks describe how complexity can arise over time. But when you look at the broader pattern, it raises a deeper question. Why does the universe allow for this balance at all? Why does it operate in a regime where both structure and variation coexist in a way that enables complexity? Again, this is not something we have a definitive answer to, but it is something we can observe. And as we observe it, we begin to notice that this balance appears across multiple levels of reality, which suggests that it may not be accidental, not in the sense of being designed, but in the sense of being intrinsic to how the universe operates. Now, there is another layer to this that becomes visible when we consider the role of the observer again. Because we are not just noticing this balance, we are part of it. Our own ability to think, to question, to reflect, arises from the same interplay of structure and uncertainty. Our brains operate through physical processes that are governed by the same laws we've been discussing. And yet from those processes emerges something that can step back, at least partially, and examine those laws. And this creates a kind of resonance between the observer and the observed. Not a mystical connection, but a structural one. We are systems within the universe that reflect the properties of the universe. And so when we find patterns, when we recognize balance, when we identify structure, we are, in a sense, recognizing aspects of the system we are part of. Now, this does not mean that our perceptions are perfectly aligned with reality. We still rely on measurement, testing, refinement. But it does suggest that our ability to understand the universe is not entirely separate from the nature of the universe itself. It arises from it. And this brings us to a quieter kind of realization, that the process of exploring the universe is not just about gathering information, it's about gradually aligning our understanding with the patterns that are already there. And that alignment is never complete, not because it fails, but because the system itself is open-ended. There is always another layer, another question, another boundary where understanding can deepen. So as you sit with all of this, without needing to resolve it, notice how the perspective has shifted. From seeing the universe as something external and fixed, to seeing it as something layered, dynamic, and partially accessible, not fully hidden, not fully revealed, but continuously unfolding, both in itself and in our understanding of it. And perhaps that's the most grounded way to approach it, not as a mystery to be solved once and for all, but as something to be explored, carefully, patiently, with an awareness of both what we know and what remains open. And as we move toward the final parts of this journey, we'll begin to settle into that perspective even more. Not by adding new concepts, but by allowing everything we've explored to come together into a quieter, more complete view. A view that doesn't try to force conclusions, but simply observes what is there. As we continue, there's a natural shift that begins to take place, not outward into new territory, but inward into how everything we've explored settles together. By now, the universe no longer feels like a collection of separate ideas. It feels more like a single, continuous system, one that can be approached from different angles, but never fully stepped outside of. And in that sense, something becomes quietly clear. Much of what we've been exploring has not just been about the universe itself, but about the way we come to understand it. Because every concept we've touched, space, time, matter, information, observation, exists not only as a feature of reality, but also as part of the framework we use to describe that reality. And that dual role matters. It means that when we talk about the universe, we are always working with models, carefully constructed representations that capture patterns, relationships, and behaviors. These models can be incredibly precise. They can predict outcomes, guide experiments, and reveal hidden structure. But they are still models. They are not the universe itself. And this is not a limitation in a negative sense. It's simply part of how knowledge works. Because the universe, in its entirety, is not something we can hold all at once. It is too vast, too layered, too interconnected. So instead, we build approximations, descriptions that are accurate within certain domains. And over time, those descriptions improve. They become more refined, more unified, more capable of explaining what we observe. But they never quite become complete, and that leads to a quieter understanding. That the goal of exploring the universe is not necessarily to arrive at a final, unchanging description, but to develop models that align more closely with the patterns we observe, models that work, models that connect, models that remain open to revision as new information becomes available. Now, when you sit with that idea for a moment, it begins to soften the expectation of a final answer. Because instead of looking for a single, complete explanation of everything, we begin to see understanding as something that evolves, something that deepens over time. And within that process, there is a kind of stability. Not in the sense that everything is fixed, but in the sense that the underlying patterns of the universe appear consistent. The laws of physics apply across vast distances. The same principles that govern particles also shape stars and galaxies. The same mathematical structures appear in different areas of study, and that consistency is what allows knowledge to build. But at the same time, there is always more. More detail, more connection, more depth. And this creates a kind of balance between what is known and what is still being explored, between certainty and openness. And as we've seen, this balance appears not just in our understanding, but in the universe itself. So the process of learning about the universe begins to mirror the structure of the universe, layered, evolving, never fully complete. Now, there is another aspect to this that becomes more noticeable the longer you consider it. Because when we explore the universe, we often focus on its scale, how large it is, how complex, how far it extends. But there is another dimension to that exploration. The fact that it is accessible at all, that from within this vast system, it is possible to observe patterns, to form theories, to test ideas, to refine understanding. And that is not something we necessarily expect from a completely arbitrary system. It suggests that the universe has a kind of internal coherence, a structure that allows it to be, at least partially, understood from within. Again, this does not imply intention or design. It simply highlights a property. that the universe is not only consistent, but interpretable. And that interpretability is what allows everything we've discussed to exist. Theories, models, observations, all of it depends on the ability to recognize patterns and relationships. Now, if we bring this back to the broader perspective, something quietly settles into place. The universe is vast, structured, and partially unknown. Our understanding of it is layered, evolving, and always incomplete. And the process of exploring it is itself part of the system. So rather than seeing the unknown as something separate, something waiting to be eliminated, we begin to see it as part of the structure. Not a gap to be closed entirely, but a space where exploration continues. And that changes the tone of the question. From, when will we fully understand the universe? To something more open. How far can understanding go, given the structure of the universe and our place within it? And that question does not demand an immediate answer. It invites a kind of steady attention, a willingness to explore without needing to resolve everything. And as you let that idea settle quietly, notice how it shifts the perspective. From trying to reach an endpoint, to simply continuing the process, observing, questioning, refining. And within that process, there is something almost calming, because it removes the pressure of final certainty and replaces it with something more sustainable. A sense that understanding is not something you arrive at once, but something you participate in. And as we move into the final part, we'll begin to gently bring this exploration to a close. Not by concluding, but by stepping back one last time and looking at the whole picture. Not to define it, but to simply see it. As we continue, everything begins to quiet down. Not because the universe itself becomes simpler, but because the need to separate, categorize, and analyze starts to ease. After moving through so many layers, space, time, matter, observation, information, limits, we reach a point where it becomes less about adding new ideas and more about letting the existing ones settle into a single, continuous perspective. And when you step back in that way, something subtle becomes noticeable. The universe does not present itself as a finished structure. It presents itself as something in motion, not just expanding in space, not just evolving over time, but unfolding in a way that allows for increasing complexity, deeper structure, and more refined understanding. And within that unfolding, there is no clear dividing line between what the universe is and how it is understood. Because everything we've explored, the models, the theories, the observations, are themselves part of the same system. They are not external descriptions, they are internal reflections. And that realization doesn't change the facts of physics, but it changes the way those facts feel. Because instead of looking at the universe as something distant and separate, it begins to feel more immediate, more connected. Not in a dramatic or exaggerated way, but in a structural sense. We are not outside observers. We are participants. Small, localized processes within a much larger system, gradually becoming aware of that system. And that awareness is not static. It evolves, just as the universe evolves. Now, this does not mean that the universe is dependent on observation. The stars, the galaxies, the structures we've discussed, they exist independently of us. But our understanding of them exists within the same framework. And so, the act of understanding becomes part of the larger pattern, a continuation of the same processes that produce structure, interaction, and complexity. And when you look at it this way, something begins to feel more consistent. Because the same themes appear at every level: emergence, relationship, layering, limits that are not absolute barriers, but transitions into new forms of understanding. And within those themes, there is a kind of stability, not a fixed endpoint, but a consistent structure that allows everything else to happen. Now, as we approach the end of this exploration, it becomes less important to hold on to specific details and more important to notice the overall shape of what we've been looking at. A universe that is vast, but not entirely accessible, structured, but not fully defined, governed by laws, but still open to deeper explanation, and within it, observers who are capable of recognizing patterns, asking questions, and refining their understanding over time. And that combination, structure and openness, law and uncertainty, observation and participation, seems to be a recurring feature, not something added on, but something built into the system itself. So rather than trying to resolve all of this into a single conclusion, it becomes more natural to simply hold it as a perspective, a way of seeing the universe that is grounded in what we know, while still allowing space for what we don't. And in that space, there is no urgency, no need to force answers, only the steady continuation of exploration. And perhaps that is where everything we've discussed naturally leads, not to a final explanation, but to a way of approaching the universe that remains open, consistent, and quietly curious. Because no matter how much we learn, there will always be another layer, another connection, another question just beyond the current edge. And that edge is not something to be closed. It is something to be approached, carefully, patiently, with an awareness that understanding is not a destination, but a process. And as you sit with that idea, letting it settle without needing to define it further, the universe begins to feel less like something distant and overwhelming, and more like something that can be explored step by step from wherever you are. As we come to the final part of this journey, there's nothing new that needs to be added. No final theory to introduce. No hidden answer waiting to be revealed at the end. Instead, what remains is something quieter, a way of seeing everything we've explored as part of a single, continuous whole. Because when you look back, slowly, without trying to organize every detail, you begin to notice that the universe never really separated itself into the categories we use to understand it. Space and time, matter and energy, observer and system, information and structure. These were ways of approaching it. Useful, necessary, precise in their own domains. But the universe itself moves seamlessly between them. At the largest scales, it stretches outward, forming patterns that echo across unimaginable distances. At the smallest scales, it shifts into probabilities, interactions, and relationships that resist simple definition. Space-time curves, time flows, or appears to, information moves, structures emerge, observers arise, and all of it happens within the same system. Not divided, not layered in isolation, but connected. And that connection doesn't need to be forced or explained all at once. It's already there, visible in the way each part reflects something about the others. The limits we encountered, the edges of observation, the uncertainty of quantum systems, the boundaries of explanation, were never obstacles in the usual sense. They were markers, indications of where one layer of understanding transitions into another. And each time we reached one of those boundaries, something interesting happened. The questions didn't end. They changed. They became deeper, more refined, more connected to the structure of the system as a whole. And that process never really stops, because the universe is not something that presents itself all at once. It reveals itself gradually, depending on how it is observed, how it is measured, how it is understood. And within that gradual unfolding, there is a kind of consistency. Not a fixed endpoint, but a stable framework that allows exploration to continue. Now, as everything settles, there is one final shift that naturally takes place. A shift away from asking what the universe is, and towards simply recognizing how it appears when observed carefully, patiently, without rushing to conclusions. It appears structured, but not rigid, knowable, but not fully known, consistent, but still open. And within it, the act of observing, of thinking, questioning, exploring, is not separate from the system. It is part of it, a continuation of the same processes that give rise to everything else. So rather than standing outside the universe and trying to define it completely, we find ourselves within it, participating in its unfolding, gradually refining our understanding as we go. And perhaps that is enough. Not as a final answer, but as a stable place to rest, because it allows the questions to remain without needing to resolve them all at once. It allows curiosity to continue without forcing certainty. And it allows the universe to be what it appears to be, vast, layered, and still, in many ways, open. So as you begin to drift, letting these ideas settle into something quieter, something less defined, notice how the perspective has shifted from trying to reach the edges of the universe to simply observing what can be seen from within it, from trying to explain everything to recognizing the patterns that are already present. And within that, there is a kind of calm, not because everything is understood, but because it doesn't need to be, all at once. The exploration continues, quietly, gradually, exactly where you are, and somewhere beyond what we've explored tonight, beyond what we can currently measure or fully describe. The universe continues as well, not waiting to be solved, just waiting to be observed, one layer at a time. And for now, that's enough.